Hello, good day. My name is Adam Christopherson. I am a math PhD student here at The Ohio State University. I work in complex and harmonic analysis, and it's my pleasure to be here with the happy YouTube presentations here. Thank you to Philip Gressman, Xiaoming Guo, Yuming Wu, Malabika Promalik, and Betsy Stovall for their kind invitation. And I'm eager to talk about some of my recent research here, so I'll pull up my screen and get moving on that. So today I'm going to talk to you about the breakdown of weak type regularity on generalized Hartogs triangles in C3. This work is joint with my advisor, Kenneth Koenig. And today's October 13th, but we're at whatever day it is. Thank you for tuning in. So as usual, we have the space of square integrable functions denoted L2 and equipped with the usual L2 norm, of course, the square root of what's on the right-hand side here. We take a look at the subset of L2 functions, which are holomorphic, and we denote that space A2, think A for analytic. And A2 is equipped with the supremum norm. And a very important result shows that the supremum norm is in fact connected to the L2 norm in the following way. So by the mean value property for holomorphic or harmonic functions, the supremum on the domain omega is dominated by the L2 norm of F, and therefore A2 of omega is a closed Hilbert subspace of L2 of omega. Now, since the evaluation functional is a bounded linear functional on A2 of omega, the Riesz representation theorem asserts that there exists a unique function, boldface B omega, it's holomorphic in Z, anti-holomorphic in W, such that point evaluation is realized by integration against this kernel, a volume integration against this kernel, B omega ZW. And for obvious reasons, this is called a reproducing Hilbert space kernel. Of course, this kernel will have a singularity along the diagonal when Z equals W. On nice domains like the unit disk in C, the kernel takes the form 1 over 1 minus Z times W bar. Of course, when Z times W bar is close to 1, that denominator is not integrable, but just barely not integrable. So this is not just a random kernel, it's a very important one. It's called the Bergman kernel, and the associated integral operator, what I have on the right-hand side of the equality, is called the Bergman projection. We'll denote the projection without the boldface, so just B. The kernel will be boldface B omega. And studying the mapping properties of this integral operator has been a very fundamental problem in several complex variables since at least about the 1970s. And the fundamental question that kind of motivated everything was, what function spaces other than L2 is this operator norm bounded on? So just as with the Hilbert transform, for example, you have a full range of LP boundedness from P equals 1 to infinity on many types of domains. So in particular, we require at minimum a C infinity smooth pseudo-convex domain with some additional assumptions on the geometry of the boundary. Now, if you're a real analyst, pseudo-convexity perhaps isn't all that important to you. It's an important condition in several complex variables. It has to do with something called the Levy form. And crucially, with pseudo-convex domains, they're preserved under biholomorphism. So if you have a pseudo-convex domain, you apply a biholomorphism to it, the output remains pseudo-convex. But I suppose it's not all that important for today. But if you do have those conditions, for example, the unit ball in Cn has those conditions, and hence you're bounded on LP from all P from 1 to infinity. Of course, you'd never be bounded on L1, you'd never be bounded on L infinity because of the singularity there. But for all the other P's, you're bounded, for example, on the unit ball. That's due to an integral estimate of Forelli and Rudin, as well as a result called Schur's lemma, which is fairly similar to Young's integral test. This also holds, for example, on strongly pseudo-convex domains. That's due to Pfefferman's asymptotic expansion of the Bergman kernel and a later result of Wang and Stein. It's true on pseudo-convex domains of finite type in C2, and due to Jeff McNeil and Nagel, Rosset, Stein, and Wenger. Finite type is another somewhat technical condition in several complex variables. It has to do with the order of contact at the boundary of the domain. It's true as well for convex domains of finite type in all dimensions due to Jeff McNeil and Elias Stein. However, that full range from 1 to infinity does not always extend in the case that omega is not smooth. The boundary of omega is not smooth, to be precise. We can see that, for example, on a very canonical, classical, non-smooth domain in C2, and it's called the Hartogs triangle. Absolute value of Z1 less than absolute value of Z2 less than 1. This is used a lot for many counterexamples and several complex variables, but this domain is bounded. It's a subset of D times D. It is pseudo-convex. It's also a Reinhardt domain, meaning that rotations of each of the variables is allowed on account of the absolute value. So being a Reinhardt domain means we have the tools of polar integration at our disposal. It's also biholomorphic to D times D star using the following map. Z1 goes to Z1 times Z2, and Z2 remains itself. D star denotes the punctured disk, so we remove the origin. However, this domain has a one shortcoming. It has a very much unsmooth boundary, particularly at the origin, where the boundary cannot even be expressed as the graph of a continuous function. Now, authors in about the early 2010s did study the LP mapping properties of the Bergman projection on H1, and this is due to Li Wei Chen and Eunice Ntuchu. They found that the Bergman projection is bounded if and only if on LP, if and only if P lies between 4/3 and 4 exclusive. Now, you note that Bergman projection is bounded automatically on L2. It's also self-adjoint, so the range of LP boundedness will always be Holder symmetric. So 3/4 plus 1/4 is 1. It'll also always be centered at P equals 2. Now, the question that where I come in is to study the endpoint weak type regularity. So what's going on at those two endpoints, in this case, 4/3 and 4. And the most suitable replacement for LP regularity is, of course, weak type regularity, which is used a lot in the Calderon-Zeeman theory. A linear operator or sublinear operator acting on an LP space is said to be weak type PP if the set or the measure of the set where the operator exceeds lambda is bounded above by constant, the LP norm of F over lambda to the P, all raised to the power P. You can sometimes change this and make the denominator power on lambda Q, but for today, we'll just keep it weak type PP. Of course, the constant C has to be independent of F. Now, if T is bounded on LP, this is simply Chebyshev's inequality, but there are a number of operators, such as the maximal function on R, that satisfies a weak type estimate, particularly a weak type 1,1 estimate, but is not bounded on L1. So, just before the pandemic, Brett Wick and Zhengwei Wu studied and characterized the weak type regularity at those endpoints, and they found that the Bergman projection is of weak type 4/4. That's the upper endpoint of LP boundedness. It is not, however, weak type 4/3, 4/3, which is the lower endpoint of LP boundedness. So that ended up being a little bit of a surprising result. So, like many things in complex analysis, we seek to generalize those results on H1. So let us consider H gamma, where instead of putting the exponents all to be 1, you put a general exponent on the first variable. So absolute value of Z1 to the gamma less than absolute value of Z2 less than 1. Now we'd like this domain to remain bounded and pseudo-convex, so we'll insist that gamma be positive. And in fact, in a moment, you'll see that we further have to insist that gamma be a positive rational number because of the following theorem of Luke Edholm and Jeff McNeil. In about 2016, they stated that if gamma is irrational, then the Bergman projection is bounded only for the trivial exponent P equals 2. If gamma is m over n, it's a positive rational number, then the Bergman projection is bounded on LP if and only if P lies in this range here at the bottom of the slide, 2m plus 2n over m plus n plus 1, 2m plus 2n over m plus n minus 1. And our earlier result from last year, in fact, characterized the weak type regularity on the so-called rational Hartogs triangles. And in fact, we confirmed that the same phenomenon observed by Wu and Wick extends to the rational Hartogs triangle. So my advisor and I showed that the Bergman projection is of weak type at the upper endpoint. It is not weak type at the lower endpoint. Don't have a live audience, so I'll preemptively ask myself a question. And the question is, does this phenomenon extend to higher dimensions? And the answer, in fact, is yes, provided you carefully define what the Hartogs triangle in C3 looks like. So let us, for example, consider the following. I'll call it H with a boldface P, Z1, Z2, Z3 in C3. And now I'm going to multiply out by the denominator of that rational number. And let's consider absolute value of Z1 to the P1, absolute value of Z2 to the P2, absolute value of Z3 to the P3, all less than 1. Without loss of generality, we can assume that the GCD of P1, P2, and P3 is equal to 1, of course. Now, I'm not the first person to consider these types of domains. In 2019, J.D. Park studied the Bergman kernel on domains of the form HP. And a few years later, Shou Zhang showed that the Bergman projection is bounded on LP if and only if P lies in this range here. So 2L over L plus D, 2L over L minus D. Capital L is the sum of the pairwise products, P1, P2 plus P1, P3 plus P2, P3. And capital D is the GCD of the pairwise products. And now that we have a range of LP boundedness, we can step in and study the weak type endpoint regularity. And that was from this year. The Bergman projection on this domain is not of weak type at the lower endpoint, 2L over L plus D. It is of weak type at the upper endpoint, which is 2L over L minus D. So the same result that was observed by Woe and Wick in H1, the same result that was observed by my advisor and myself for the rational Hartogs triangle, and in fact for these three-dimensional analogs as well, still holds. Kind of an interesting and somewhat surprising one-sided weak type estimate. So just for the harmonic analysts audience, I wanted to focus on proving the failure of a weak type estimate. And it's a little bit of an unexpected, or it's at least a little bit of a calculation you don't see every day. So how does one prove that a weak type estimate fails? Well, one has to exhibit counterexample functions f lambda and constant c lambda, with c lambda blowing up, such that the weak type inequality is reversed. So the set where the Bergman projection exceeds lambda is greater than the LP norm of f over lambda all raised to the power p, and the constant on the right-hand side of the inequality is blowing up, and therefore there is no hope of that weak type estimate ever holding. And what that counterexample function ends up looking like is essentially a three-parameter anti-holomorphic rotation function. So it's going to depend on lambda, of course, and it's going to take the following form. So z1 bar to the minus k, absolute value of z1 to the k. Same thing in the z2. So z2 bar to the minus l, absolute value of z2 to the l. z3 bar to the a3, and absolute value of z3 to the b3. K and l must be non-negative integers. A3 must be a positive integer, and B3 is a real number that is allowed to depend, and in fact must depend, on lambda. Of course, to avoid dividing by 0, we would insist that this function be 0 if Z1 or Z2 are equal to 0. And it's worth mentioning that this example is loosely based on the ones used by Brett Wick and Cheng-Wei Wo in 2020, and my advisor and myself last year. Now, one thing that's curious is that if you take a look at the formula for our function f at the top of the slide, the minus k and k will cancel each other out when we compute the LP norm, and likewise, the minus L and L will cancel each other out. So you, in fact, will not see the k or the L when we calculate the LP norm. That's just a straightforward application of polar integration. All you'll see are the A3 and B3, and you'll end up with the following, provided that the second factor in the denominator is positive. And of course, like I mentioned, the norm doesn't depend on K or L. Now, finding a closed form for the Bergman kernel on HP is actually a rather difficult task. That was done in large part by J.D. Park. However, the good news for us today is that we don't actually need a closed form of the Bergman kernel because we have an alternate characterization that ends up being very powerful. And let me tell you what that is. This is due to a Rees-Fisher theorem, and it shows that the Bergman kernel, if a closed form isn't obtainable, you can also realize it by an infinite series of the orthonormal basis elements of the Bergman space A2. So more precisely, if you have an orthonormal basis for A2, a countable orthonormal basis phi j, then the Bergman kernel is simply phi j in the holomorphic variable z, phi j w bar in the anti-holomorphic variable w. Now, this characterization is not used very often in complex analysis because it's not entirely clear what an orthonormal basis for A2 would be, and it's certainly not entirely clear how you would be able to sum them. But this will end up being very useful for us today because due to the fact that our domain is a Reinhardt domain, we can take suitably normalized three-variable monomials to be our orthonormal basis. So in particular, W1 to the alpha 1, W2 to the alpha 2, W3 to the alpha 3, they have to be orthonormal. So as long as you normalize, this will be allowable. Now, alpha 1, alpha 2, and alpha 3, they're monomials, so they must be integers. Of course, if they're all positive, there's no issue here, but some negative values are allowed as long as the monomial is still square integrable. And I'll tell you exactly what those conditions are in just a moment. But using that theorem, we can calculate the Bergman projection of our function here. I've changed variables now, so W is the integration variable. This is our function here, and these are our monomials alpha 1, alpha 2, and alpha 3. I've said the alphas, that's the multi-index, it belongs to A, and I'll tell you what those conditions are just momentarily. The set A of allowable indices are the triples that satisfy the following three conditions. So as long as these three conditions down here are satisfied, then the desired exponents are larger than -2, and therefore square integrable near the origin. The good news is that this series, which looks a little bit intimidating, ends up being 0 in all but one case. So these terms will all vanish unless alpha 1 equals k, alpha 2 equals L, and alpha 3 equals minus A3. Why is that? Well, because you need the W bars to cancel. And the only way W1 bar cancels is if it cancels out with his friend over here. So K, W2 to the alpha 2, well, you need that to cancel out with this minus L here. And you have W3 to the alpha 3, you need that to cancel out with A3. And that only happens precisely when alpha 1 is K, alpha 2 is L, and alpha 3 is minus A3. Now, since alpha 1, alpha 2 are at the very least integers, it must also be the case that K, L, and A3 are likewise integers. So let's talk about how one would select those. Of course, if P1 is P2 and that's also equal to 1, then we actually don't need the L or the K. They can both be 0. And our function would only end up depending on the last variable, Z3. This is what happens in the proof of Brett Woe and Wick back in 2020. And the reason is that because if P1 is P2 and that's equal to 1, our domain, which I've written here for you, is actually biholomorphic to D times D star times D star, which is basically the punctured tridisk. And in that case, the computations are very straightforward. In the more difficult case, when P1 or P2 is not equal to 1, then their product must be larger than 1. And we can choose positive integers L and K such that L P1 P3 plus K P2 P3 plus L minus D is a multiple of P1 P2. Rearranging slightly, you have L plus 1 P1 P3 plus K plus 1 P2 P3 is equivalent to D mod P1 P2, so D plus a multiple of P1 P2. And just to remind you, capital D was the GCD of P1 P2 of the pairwise product. So P1 P3, P2 P3, P1 P2. Now, when is this solvable? Well, in fact, we do need to appeal to a result of number theory, and that is due to Bézou's identity. In fact, that modular arithmetic equation is solvable. So there would exist x1, x2, and x3 integers such that x1 P1 P3 plus x2 P2 P3 plus x3 P1 P2 is equal to D. This is the 3-parameter version of Bézou's identity. And in particular, if you just consider those first two terms, it's equivalent to D plus a integer multiple of P1 P2. Now, adding a multiple of P1 P2 to both sides if necessary, we can safely assume that x1 and x2 are positive integers. And therefore, L would be x1 minus 1, K equals x2 minus 1. That would ensure that K and L are integers as well. Now, those conditions for the A need to be satisfied. And of course they are, because alpha 1 is k, that's positive. And L plus a positive number is also positive because L is positive. And finally, A is chosen strategically. So that's L P1 P3 plus K P2 P3 plus L minus capital D. Now the numerator of A3 has been chosen to be a positive integer multiple of P1 P2. So in particular, when you divide by P1 P2, you remain a positive integer as desired. And that's basically what I've said here. So A3 is a positive integer precisely because of the way we chose L and K. And that shows that the triple does in fact lie in A, the set of allowable indices. Consequently, we can go back to that crazy series, pull out those powers of Z1, Z2, Z3. You can also pull out the normalization constant, which actually is a constant in this case, which I'll call C prime. And then you just have to polar integrate that, which is going to be pretty straightforward. By construction, this middle term is a positive number. L is positive, and you just added some positive things to it. So that's a bona fide positive constant. B3 is the final parameter for us to choose, and it appears here in the final term. So we can finally select that. Let us call gamma this middle term here, and simply take B3 to be lambda to the minus delta minus P3 over P2 gamma minus 2, so that this last term in the denominator is simply lambda to the minus delta. And if you bring that up to the numerator, it's lambda to the positive delta. Delta is going to be a positive number to be chosen just shortly. And like I said, with this choice, you have the Bergman projection being a constant times those powers of Z1, Z2, Z3 with lambda to the positive delta brought up to the numerator. And if you go back to a few slides ago, the LP norm of F to the power P is also a positive multiple of lambda to the delta. And all the constants here are independent of lambda. So we're ready to go. So we're not going to do the weak type estimate on the entire HP Hartogs triangle. Let us just consider a subset of HP in which the middle two variables, so Z1 to the P1, Z2 to the P2, are comparable to the absolute value of Z3 to the P3. So let's define H tilde in this way. So if you can show that the weak type estimate fails on H tilde, then it would also fail on HP. And hence, you can go ahead and start writing that weak type estimate. So the set where the Bergman projection exceeds lambda, well, we've replaced the Bergman projection with what we've estimated it to be. We can now replace the powers, so Z1 and Z3 can now be disposed of because they're both comparable to absolute value of Z3 suitably to a suitable power. Then we can finally isolate the absolute value of Z3 for our polar integration. And we end up with this as follows. So lambda, divide that over, you get lambda to the delta minus 1 with a slightly crazy power. However, that power ends up just being absolute value of Z3 less than some constant, lambda to the delta minus 1, P1, P2 over L minus D. L minus D is the denominator of P prime, where P prime is the Holder conjugate to P, and that'll end up actually being important momentarily. Notice a small piece of housekeeping that if delta is less than 1, then you have absolute value of Z3 less than lambda to a negative power, and that would ensure that absolute value of Z3 is less than 1 for lambda sufficiently large. So we will have to insist that delta be positive, but no more than 1. And for such large enough lambda, the weak type norm ends up being equal to this polar integration, where eta is as follows. It took me a few minutes to convince myself that eta was actually non-negative, but it definitely is. And finally, we can polar integrate this one more time. So P1, P2, L minus D. In fact, you'll get a P1, P2 in the denominator of the outside exponent, which will cancel out perfectly. And in fact, what you end up with, and the power of lambda, is lambda to the delta minus 1 times the sum of the pairwise products over L minus D. That is precisely the Holder conjugate, P prime. So this weak type estimate is comparable to lambda to the delta minus 1 P prime. Now, P prime is larger than P. So if you can peel away those lambda to the delta power here, so this is lambda to the delta, lambda to the P, and what you're left with is some leftover powers of lambda. And if delta is chosen sufficiently close to 1, so in particular in this range here, then these remaining powers of delta, you'll be left with a remaining positive power of delta, and or a positive power of lambda, I should say. And as lambda goes to infinity, that remaining positive power will go to infinity, and the weak type estimate will fail. And that would prove it. So a little bit of an interesting calculation. I don't think we've seen very many, at least there's not too many examples in the literature of the failure of a weak type estimate. So that's why I chose to talk to you about it today. Now, we also have to prove a positive result in our work. Doing so requires kernel estimates on the Bergman kernel and dividing into cases. What essentially has to happen is we take an integral on the Hartogs triangle HP and use branch cuts to transform it into an integral, or more likely a sum of integrals on the tri-disk. So d times d times d, and we end up doing an integral estimate on that domain there. So we're looking to extend this work to other types of domains in CN, presently working on that. And we're also looking at different types of domains, including domains characterized by other authors like Liwei Chen, and we'll end up seeing where that goes. So thank you very much for your interest. My email here and my advisor's email, we're always happy to hear questions, comments, and conjectures. But definitely a little bit of an interesting result. We're always on the lookout for other types of domains where this might not be true. So it seems like failure of a weak type estimate at the lower endpoint, success of a weak type estimate at the upper endpoint. And the question is, are there any types of domains where that might be reversed? Hopefully I'll report back to you on that shortly. So thank you. Thank you for the invitation. It's been great speaking to you, and thank you.